We begin with a definition. Let E be an extension of a field F. An element alpha in E is called primitive if the field E is generated by alpha over F. Let's consider the following example/exercise. Take F to be the field of rational numbers and let E be its extension, where we adjoin root of 2 and root of 3. Take alpha to be square root of 2 plus square root of 3. We claim that this element alpha is primitive. So that is the extension of Q with square root of 2 plus square root of 3 will contain both square root of 2 and square root of 3. And to prove this, show that minimal polynomial of alpha has degree 4. This will give us that the dimension of Q of alpha over Q is equal to 4. But we also know that dimension of E over Q is also equal to 4. This shows that we have this equality. And now we state our main theorem. Let E be a finite and separable extension. Then E contains a primitive element. That is, there exists gamma in E such that E is equal to f of gamma. So we make the following remark, that it is sufficient to consider the case when E is the extension of F with two elements, alpha and beta. In general, we know that E is generated over F by a finite number of elements, but then repeatedly applying the result for two-element extensions, we will obtain the claim of this theorem. Another remark that we make: if we have a finite and separable extension, and K is an intermediate subfield, then both extension K over F and E over K are separable. This is based on the following simple observation. Separability of the extension means that the separable degree of E over F is equal to the usual degree of E over F. And both degrees are multiplicative. So this means that E over F is equal to the product of degree of E over K times degree of K over F. And the same is true for separable degree. We also know that the separable degree does not exceed the usual degree. Then the equality of the left-hand sides in these formulas implies the equality for each factor. This allows us to reduce this theorem to the case when E is generated by two elements over F. So now we assume that E is generated by elements alpha and beta, and that the degree of E over F is equal to n. And we'll also assume that F is infinite, because for finite fields, we already know that this result holds. Recall that the separable degree is the number of embeddings of E into the algebraic closure of F. And let sigma 1 through sigma n be distinct embeddings of E into F bar. Since E is generated by elements alpha and beta, then each sigma j is determined by its values on these elements. Let us construct the following polynomial. P of x be the product over I different from j, sigma I of beta minus sigma j of beta times x minus sigma I of alpha minus sigma j of alpha. By our previous remark, each factor in this product is non-zero, because these two coefficients cannot be simultaneously zero. So this tells us that P of x is a non-zero polynomial, and since our field is infinite, this tells us that there exists a constant c in F such that P of c is not equal to 0, since a polynomial can have only finitely many roots. This tells us that when we evaluate x at c, each factor in this product is going to be non-zero. This can be expressed in the following way, that for all I different from j, sigma I of c beta minus alpha is not equal to sigma j of c beta minus alpha. This gives us a primitive element. So we set gamma to be c beta minus alpha, and what we see is that sigma 1 of gamma through sigma n of gamma are all distinct. This implies that there exist n embeddings of f of gamma into f bar, and hence the degree of f of gamma over f is greater or equal to n. But f of gamma is a subfield in E. This implies that E is equal to f of gamma, and gamma is a primitive element. We use primitive elements when we are trying to prove something about field extensions. It is convenient to think that a given field extension is generated by a single element. When we do calculations in Galois theory, most of the time we do the opposite. We are trying to find as many intermediate subfields as possible and then break down the complexity of the problem into smaller pieces. Let us give an example of a finite field extension without a primitive element. Clearly, such an example must be in characteristic P, because in characteristic 0, every extension is separable. And it should involve infinite fields, because we know that finite fields are separable over ZP. So we'll let F to be ZP with TS. So these are rational functions over Zp in two variables. And let E be the following extension of f. So we adjoin two elements, alpha and beta, such that alpha to the power of p is equal to t, and beta to the power of p is equal to s. So we adjoin to f pth root of t and pth root of s. It is easy to see that the degree of this extension is p squared. The key observation for this example is that for every gamma in this field, gamma to the power of p belongs to f. This follows from the fact that raising to the power of p preserves addition and multiplication. And from here, we can easily see that for every gamma in E, which is not in f, the degree of f of gamma over f is equal to p. So no element gamma will give us degree p squared. And we conclude that E has no primitive elements. Next, let us prove the following theorem. Let f of alpha be a finite extension of f. Then there exists only a finite number of intermediate subfields k, which are in between f and f of alpha. Let us give a proof. Let p of x be the minimal polynomial of alpha over f, and let gk of x be the minimal polynomial of alpha over k. Then gk of x is a factor in p of x in the ring E of x, where we denote by E our field extension f alpha. Since both polynomials p of x and gk of x by definitions are monic, they can be only finitely many choices for gk of x. Let us show that the field k is completely determined by the polynomial gk of x. Let k0 be the subfield in E generated by the coefficients of the polynomial gk of x. Since by construction this polynomial has coefficients in k, we have that k0 is a subfield inside k. And since gk is irreducible in k of x, it is also irreducible in k0 of x, because every factorization over k0 is also a factorization over k. This tells us that degree of alpha over k0 is equal to degree of alpha over k. And from here, we get the degree of E over k0 is equal to degree of E over k, which implies that degree of k over k0 is equal to 1, and so k is equal to k0. This proves that the field k is completely determined by the polynomial gk, and since we can choose gk only in finitely many ways, we conclude that there could be only finitely many intermediate subfields between f and f of alpha. Finally, let us show that in our previous example, we have a finite field extension with infinitely many intermediate subfields. Again, as our base field, we take the field of rational functions over Zp in two variables, and we take as E its extension with elements alpha and beta, where alpha to the power p is equal to s and beta to the power p is equal to t. So here a basis of E over f consists of alpha to the power I times beta to the power j, where I and j go from 0 to p minus 1. The field E admits a grading by a group Zp. This means that as a vector space, E decomposes into the direct sum of E0 plus E1 plus E2 plus E p minus 1, where f sits in the component E0, alpha and beta belong to component E1, and we have a multiplicative property that EI multiplied with EJ will belong to EI plus j mod p. The reason that this works is that these relations are homogeneous with respect to this grading. Both alpha to the power p and s will belong to component E0. For each constant c in f, consider element gamma, which is alpha plus beta times c. We already saw that the basis of f of gamma over f is 1 gamma gamma squared up to gamma to the p minus 1. But what we have here is that gamma belongs to the component E1 and gamma to the power of j belongs to the component EJ. This tells us that the field f gamma is also graded with one-dimensional homogeneous components. And the intersection of f gamma with E1 is just all multiples of gamma. Since alpha and beta are linearly independent over f, we conclude that if C is not equal to C prime, then the space f gamma is not equal to the space f gamma prime, which implies that these two fields, f of gamma and f of gamma primes, are distinct. Since the field f is infinite, we have infinitely many choices for the constant C, and thus we obtain infinitely many subfields that are intermediate between f and E.